Okay, welcome back, dear students. So we were talking about the rectification. Now, as we have discussed the half wave rectifier, it is turn to discuss the full wave rectifier, because here both the cycles of an input waveform are reversed in direction. The one is already in the same direction, but the other one, which was in the opposite direction, like if you have this waveform. So in half wave rectifier, the positive cycle will be allowed to flow, while in negative turn, it will behave as a closed switch. This is for the half wave rectifier HWR. Sorry, this was for a half wave rectifier. For a full wave rectifier, the approach will be slightly different, because now the positive half will be allowed to flow, while the negative half will be given a separate direction, or the different direction than its original direction, and the direction will be reversed. So it will be like this one. As here we know that there is no current here, but the full wave rectification case, this space is filled with the same waveform. So the efficiency of the rectification is increased. You can see that the average value is now increased from 0.3182 to 0.636, because now the both the waveforms are available, and the average is again increased. So the rectification can be improved by using a full wave rectifier. Okay, we have discussed it, and let's move towards the two configurations which are usually used in full wave rectification case. Okay, the first one is a bridge rectifier, which is shown here. In this bridge, we have bridge configuration where the two opposite diodes are in the same direction. This diode and D1 and D4 are in the same direction, while D2 and D3, these are in the same direction. So what will happen for the positive flow? What will happen? This voltage is here, and the terminals and all the and the input terminals will have the polarity like this one. Okay, for this polarity, this will again be positive. Okay, so for positive case, the diode appear here a will behave as a closed switch, because now for this polarity, this will be a forward bias, while the other diode, which is available here, this one, will behave as a open switch, because now you can see that this is positive, and the positive is connected with the cathode of this diode. So that's why this will behave as a open switch. So the current will move here, and here it will come. This polarity will be positive, and this is again positive now. So you can see that again here in this case, this diode is again reverse bias. If this is reverse bias, there is no way for a current to flow here. So this current will flow through this resistor, and it will again come here. This diode is again a forward bias, and the current direction will be this one. And in this resistor, across this resistor, the current will flow like this. Similarly, for the negative reverse bias case, the terminal will behave like negative here and positive here. When this negative will come here, so this diode will behave as a positive, as a forward bias. Similarly, if you want to see like from here, this diode will behave like a open switch, because this is now reverse bias. This is the short switch, because this is now the forward bias region. The current will flow from here and then here. Okay, then here it will come here, and here this diode will become a short circuit because of forward biasing, and the current will flow from here like this one. So the circuit will be completed like this one. In both of these scenarios, you can see that the current initially was flowing in this direction. Okay, This was the current direction in first case, while in the second case you can see that the current was coming from here and again coming in then coming flowing in the same direction. So the direction of the current is again same. So you can see that the due to this same direction current, the waveform will be like this one. Waveforms will be like this one because now the currents are flowing in the same direction. So that's why we will have two waves in the same direction, and that's it. Okay, these are basically the four diodes which are connected in a bridge configuration, and these are giving us the full wave rectification. I think it is clear because now here the only load resistor, the only load resistor is this one. Okay, this is the load resistor across which we have seen the direction of the current, and in this direction the voltage waveform will be like this one. And in these in this full wave rectification, the value of the average voltage will be 0.636. Okay, so I think it's understandable. So let's move on. This is another rectifier which is called the center tape rectifier. Okay, so this is called a center tape full rectifier because now here that the input transformer is basically centrally taped, and the load resistor is connected here. For the positive cycle, this terminal will become positive and this will become negative, and current will flow in this direction. Okay, this will be the flow of the current. For the negative cycle, this will be the negative one while this will be the positive one. So the current again will flow in this direction. So you can again see that the flow of current across this diode is again similar. So that's why the current direction will be this and this one. So that's why this is again called a center tape full wave rectifier, and the value of average voltage will be this one. Okay, so I think this is again understandable. Let's move on. This is the circuit, and this is basically a simple question which is asked to find the waveform from these diodes. Please take a look, and if you guys have any difficulty, ask me. What is this asking you to find? Determine the output waveform for the network of figure 2.64 and calculate the output DC level required PIV for each diode. Okay, you have to find the peak inverse voltage in this scenario. Basically, what is this? Here we have a bridge circuit, but in this bridge circuit we have two diodes. For the positive 10 volts peak voltage sinusoid signal, we have the positive cycle, and for this positive cycle this diode will be, so when it will be modeled like this one, the current will flow here. When the current will reach here, it will be divided in these 2 points. One will flow through this one and the other will flow through this one. So this circuit is basically this one. Okay, these two, you can see that here are basically in series configuration because the same amount is flowing here from both of these resistors. So that's why these are basically in series configurations. And what you want to find out, you want to find out the voltage across this resistor. Let me remove all this. Okay, you want to find out the you have to find out the waveforms from this resistor. Okay, so this resistor is this one. This is the resistor. How can you find it out? You can find it out here, and here you will have some voltage developed. This is the overall voltage which is flowing from here. This is 10 volt, while these are 2 ohm resistors. If the 10 volts is available here, so from the voltage divider sorry, from the voltage divider law, you can find out the voltage V naught across this one, which will be V naught equal to V naught is equal to 2 kilo ohm divided by 2 plus 2 kilo ohm. What is 2 plus 2? What is 2 plus 2? Because these two are in series configuration. So 2 kilo ohm plus 2 kilo ohm is the total equivalent resistance we have to write here. What is this? 2 kilo ohm is basically the resistance of this circuit. Kilos are basically cancelled with each other in denominator and numerator, and this will be multiplied with the total voltage, that is 10 volts. Okay, this will be the peak voltage. This will be equal to 10 volts. So from here you can easily calculate the value of this peak voltage as 5 volts. So this 5 volt will have this value. Okay. Uh, Similarly for the reverse direction, because for the reverse direction, this diode will behave as a open switch, while this one will behave as a short switch, and the same waveform will be generated here like this one. This is again a full wave rectifier, but the value of the input voltage, peak voltage, will be halved here. How can it be halved? By this formula. Okay, so this one. How can you find the average voltage? You can find the average DC voltage by this formula, which is this one, and we have seen that 0.636 is the average voltage we have earlier on, like this one. Okay, this is the formula for finding the average or DC value, which is 0.636, and the same formula is used here. Okay, the same formula used here. You have the peak value 5 volts and is calculated here. So that is overall procedure for this question, and you can see. Okay, let's move on. So this is the summary of the rectifier circuits. We have discussed a half-wave rectifier, which is the which is this one. Okay, so we have discussed the rectifier circuits. For the rectifier circuits, we have discussed a half-wave rectifier, and we have seen that the value of this DC, or the average value, is equal to 0.318 times the value of the peak voltage value. Similarly, the realistic value, if you consider the drop across a diode, so that drop will be minus from the uh, DC input value, DC output value, which we have obtained from the half wave rectifier. Similarly, for the bridge wave rectifier, the value of the um, ideal VDC is 0.636 times Vm. What is Vm again? Vm is the peak value of the AC voltage, which is written here. And as we have 4 diodes, and each two of the diodes are taking part in each conduction cycle. So that's why we are removing 2 multiplied by zero point 0.7 volts from 8.636 0.66 average value. In a center tape diode, we have 2 diodes, and each of the diode is taking part in the conduction cycle. So that's why we are removing 0.7 from the 0.63 time V of M. So in center tape rectifier circuit, the value of the average voltage will be higher than the bridge rectifier, but the efficiency of a bridge rectifier is higher than center tape transformer. Okay, so let's move on. Diode clippers. It is another application of a diode, which we have to cover before a bit term. So what is basically clipper? Clipper basically clip off or remove some part of a waveform, and this is the application of a diode. If you talk about a series clipper, this is a series clipper, and if you apply this circuit here, what will happen from this for this positive cycle? It will behave as a short circuit and will allow this positive cycle to move here. This is basically a rectifier, and this will be moved here. For the negative cycle, this diode will behave as a open circuit, and no negative cycle will be moved through this one, because now this is an open circuit. So that's why it is clipping the negative cycle of this waveform. Similarly, if you apply here again, only the positive cycle will be moved, while the negative cycle will not be allowed to move here. Similarly, if you have another configuration like this one, if the configuration is like this one, okay, this is the configuration, and you are making it flow from this one, what will happen now? Here you see that for the positive cycle it will behave as an open circuit, while the for the negative cycle it will behave as a short circuit. So only the negative, this one, will be allowed to move here, but this will not be allowed to move here in this configuration. Okay, this is opposite than this one. This is a series clipper, and here um, no positive cycle will be allowed to move here, because for all the positive cycles this diode will behave as an open switch. Similarly, for this uh, waveform, this this will not be allowed to move, while only this will be allowed to move, because now you can see that this is in reverse direction than this one. These two are in reverse direction. That's why their functionality is also reverse. This is a diode clipper, and this is the series clipper configuration. If you want to use a silicon diode, so in output region the value of this V naught will be equal to V naught minus 0.7. If you want to use the real conditions, similarly here this will be equal to V minus 0.7 in the output case, but in ideal case the values will remain the same. This is the diode clipper, series diode clipper. Let's move to the parallel clippers. This is a parallel clipper, and in parallel clipper what will happen? Parallel clipper will behave uh, opposite opposite to the series clipper. Like here, if you have this waveform and it is applied here, so this for the positive cycle this will be positive, this will be negative, all the current will move here, and here when the current will come, all the current will have this way to move, and it will become here for the positive cycle. So this will behave as a short circuit. Okay, you know that what is the voltage drop across any short circuit? That is 0 volts. So for the positive cycle this will be 0 volts, and that's why at the output we will have 0 waveform. For the negative waveform what will happen? For the negative waveform what will happen? This will be negative, while this will be positive. For the negative, this will come here, and here again the voltage will be negative, while this will be positive. So this will become an open switch. For the open switch, there will be overall voltage drop here. Okay, overall voltage drop will be here, and here we will have this waveform. So this waveform will be passed through here, because there is no way to move here. So we will have a maximum waveform or maximum voltage here, and that would be this one. Similarly, when this is passed here for the positive cycle, this diode will become a short switch. So for a short switch this will be 0, while for the negative cycle this will become an open switch, and for the open switch all the voltage will be dropped here, because this will behave as an open circuit, and across the open circuit we will have maximum voltage drop. So the voltage here will be this one. So I think it is understandable. Similarly, if you induce this parallel configuration, okay, this one opposite to the first one, this is our, so the configuration will have the opposite functionality than this one. Please try this one and see what will happen here. This is for your practice. and see what will happen here, and it will behave as an opposite to this one. Okay, and then this, if the waveforms are in this direction, in this circuit the waveforms will be different at the output level. So these series and parallel clippers we have discussed here, these are for your, this is the course up to your midterm. Please take a look at it, take a good look at your examples, take a good look at the exercise questions, and we will come back to the clampers, clipper circuits, and bias clippers after your midterm. I will inshallah see you in the class, and if you guys have any question, we will discuss in your class as well. So till then, take care of yourself,